Hello and welcome you all to the 30th lecture of this NPTEL course where we are discussing the beauty of the standard model of particle physics. And today we are making it exactly the halfway, and we are very happy that we have been going very well so far, and we have discussed the very important aspects of what we call the quantum electrodynamics, and we have developed the interactions and then developed the Feynman graphs and then computed the cross sections and so on and so forth. Today we are going to discuss another interesting aspect which also marks the triumph of the quantum electrodynamics or QED, and that is actually lying in the electromagnetic moments of the fermions. Okay? So, let us get started. So, electromagnetic moments is something that you are actually already familiar to from your basic electromagnetism courses and so on. But once we are talking about the quantum expectation values, we have to talk about the parity properties before. So, let us actually see how exactly we can define them. So, the parity of the electric moments is defined by minus 1 to the power L. Now, you can ask that where L is essentially defines, so for example, L equal to 0 defines monopole, L equal to 1 defines dipole, L equal to 2 defines quadrupole, okay? And parity is defined by minus 1 to the power L. Now, you will ask that why this rule is applicable to the electric moments. Let us remind ourselves of the definition of the dipole moment. The dipole moment for a set of charges which has charge qi, which are spaced at positions ri, say for example, P is defined by sum over I qi ri. Now, under parity what happens that r actually goes to minus r. So, you can say that the dipole moment goes to minus P. So, P goes to minus P, or this is odd under parity. So, therefore, what we have to make sure that the dipole remains odd under parity. So, minus 1 to the power L, where L equal to 1, you see that this becomes actually odd under parity, and so therefore, the monopole will be L equal to 0 and quadrupole will be L equal to 2. You can visualize it like that. On the other hand, when we think of parity of magnetic moment, the parity transformation will be given by minus 1 to the power L plus 1, where L equal to 0 once again for monopole, L equal to 1 for dipole, and L equal to 2 for quadrupole. Now, this is different. Why? Because remind of the magnetic dipole moment, and this is, you can also define it like half I integral of r cross dl, or I into a, so to say, or you can also define it like q into r cross v. So, when you take the parity, because both r goes to minus r and v goes to minus v, the mu, the magnetic dipole moment, that actually remains even, and that justifies the transformation that we have defined by minus 1 to the power L plus 1. Now, there is also an important point that why parity is important for any electrical moments or magnetic moments that we are actually trying to identify for different either fundamental particles or materials. So, the quantum mechanically what we do, that we actually find out the expectation value. Now, what is the definition of the expectation value? This is actually psi star O psi. So, any operator or any observable, so to say, its expectation value is defined by psi star O psi integrated over a volume dV, and this integral essentially extends from something like minus a to plus a. Okay. Now, the point is, if this object O for which the expectation value is being evaluated, if that is odd under parity, then basically it will flip sign for minus a or to 0, or negative spatial dimensions, and so therefore, it will actually go to 0. So, any operator which is odd under parity will essentially have a 0 expectation value, and so therefore, you can say that we can have electric electric dipole moment or magnetic monopole moment will be actually 0 according to this property. Okay? So, this is interesting. On the other hand, electric monopole moment, say for example, for a nucleus, if I have to find out with atomic number Z, then what will be that? This will be the total charge content in it, which will be Z into E. But is it that obvious? If I want to find the first non-zero magnetic moment, which will be magnetic dipole moment, right? So, what will be the magnetic dipole moment, which is the leading order magnetic moment for any fundamental particle? That is the question that we would like to try to find the answer to. Now, in order to do that, let us start from the classical idea of how you can find the magnetic dipole moment. So, suppose you have a current carrying loop which is carrying a current I, and the magnetic dipole moment mu is therefore I into A. A is basically the area. Okay. So, you can also therefore say that if this I can be defined by essentially E by T, where T is essentially 2 pi by omega or 2 pi r by v, where r defines the radii of the circle, v defines the velocity of the particle, right. So, therefore, and on the other hand A is pi r square. So, the magnitude of this mu can be simply written as E v by 2 pi r into pi r square, which is essentially E v r by 2, or you can also say that this is nothing but E by 2 m into m v r. Now, what is m v r? You all remember that this is nothing but the orbital angular momentum, right, m v r. So, this is p cross r. So, that is what is defined as the orbital angular momentum, or L. So, this is essentially E by 2 m into L. Now, quantum mechanically, when we have to convert this to an operator, we can say that the mu L operator will be E by 2 m L operator, or mu Lz operator will be E by 2 m into Lz operator, and so on, right. And then you can try to find what are the possible eigenvalues and eigenstates, and say for example, these spherical harmonics y l m l, these are eigenstates of mu Lz, and you can say that when you operate this is going to essentially give you ml h cross, and this ml represents the magnetic quantum numbers which vary from minus L to plus L, and this what defines your mu Lz, right. So, mu Lz will be therefore E h cross by 2 m into ml. You can also define it this quantity E h cross by 2 m by what you call the nuclear magneton for the nuclear physics, or Bohr magneton for the atomic physics, and so on. And so, you can also write that this mu n is nothing but GL into mu n into ml, where this G is what is called the Landé-G factor, or the G factor associated with the orbital angular momentum, right. So, for example, GL will be equal to 1 for proton, and GL will be actually equal to 0 for neutron, just because that the neutron does not have an electromagnetic charge. So, the orbital magnetic moment associated with it will be identically 0. Similarly, now you can also define the magnetic moment associated with the spin or intrinsic angular momentum, and you can similarly define that mu s z operator acting on the eigenstate. Let us define it like chi half ms will give you the eigenvalue mu s z, and this mu s can also be represented by Gs into nuclear magneton mu n into s, or mu s z will be Gs into mu n into ms, where ms will be defining the what you call the magnetic quantum number associated with the intrinsic angular momentum or the spin, and the Gs will be the corresponding spin G factor, or what you call the gyromagnetic ratio. Now, the interesting point is that for spin half particles, or for fermions essentially, one can actually calculate that this Gs at the tree level is identically equal to 2, and this follows basically from the Dirac equation. And so therefore, this is an interesting consequence and an important one, and we would like to verify this property for all the fundamental particles or all the fundamental fermions, so to say, whether the Gs is exactly equal to 2 or not, right. So, in order to do that, what we will do, that we will go back to the Dirac equation and see how exactly we can write the Dirac equation with the electromagnetic interaction. Just the free equation won't do, because we need the interaction with the photon in order to actually find this spin G factor. Okay. So, let us write the Dirac equation with electromagnetic interaction. That will be what? Gamma mu I del mu. Now, there will be an additional piece which will be proportional to the charge q of the particle and with the photon field mu minus m into psi is equal to 0. So, this is basically your Dirac equation when it talks to electromagnetic interaction or the photon. Let us take a non-relativistic limit of the Dirac equation. So, non-relativistic limit matlab kya? Ki when the momentum of the particle is much less than the energy of the particle. Now, in general, if you remember that the spinorial solution of this Dirac equation like psi xt can be in terms of the particle spinor u e p into the wave function part, which is simply e to the power I p x minus e t, right. Now, you assume that if this p is way less than your e, then how you can write this psi xt? This will be simply u e p, and I drop this part p dot x part and I simply write the phase part as e to the power minus I e t. And I can also involve a two component notation for psi plus and psi minus. These are the two component spinors, so to say. So, I can write this u e p as psi plus psi minus e to the power minus I e t, correct. Now, what I am going to do, that I am going to use this form of psi x t in the non-relativistic limit, and then I am going to put it back into this Dirac equation with interaction of the electromagnetism. So, this is the one, gamma mu I del mu minus q a mu minus m into psi equal to 0, and what I am going to do, that I am going to split it into basically time and space components. So, therefore, this first term will be gamma 0 I del t minus q phi, because you remember that your a mu was essentially this phi comma a, right. So, this is the 4 vector that you actually associate with a mu. Now, so therefore, the second term is plus gamma I del plus q a minus m, and then this part which is psi, and that is psi plus psi minus e to the power minus I e t equal to 0. What is gamma 0 in the Dirac-Pauli representation? This is actually gamma 0 equal to beta, which is actually 1 0 0 minus 1, and what is gamma I? This is actually 0 sigma I minus sigma I 0. So, if I put this matrix forms and also take this derivative del t acting on this guy, and then what happens? This actually gives you a 2 cross 2 matrix form, where each individual is also a 2 cross 2 matrix. So, it is in general a 4 cross 4 matrix, but we are writing it in the form of 2 cross 2 matrix. And then what exactly the form is? This is like, the first is, you see that this gamma 0 has 1 here, and this del t is going to bring an I minus I e from here, which gets multiplied with this e I, and that brings you a factor of e. So, this is e minus m minus q phi. So, this is the term that you actually have. So, this is the first term, and this term, the off diagonal entry is going to be sigma dot I del plus q a. Here this is minus sigma dot I del plus q a, and this part, the last 2 cross 2 blob of this 4 cross 4 matrix will be minus of e plus m minus q phi, and this is just a simple matrix multiplication. You can do it very easily, but I urge you to check it explicitly. So, this acting on psi plus psi minus, giving you equal to 0. Now, we can do a simple matrix multiplication also, and then I can write it in two different equations, like the first will be E minus m minus q phi multiplied with psi plus sigma dot I del plus q a, this is multiplied with psi minus, this is giving you 0, and the next term will be minus sigma dot I del plus q a multiplied with psi plus, which is actually this term, and the minus I have eaten up, and then there is another minus sign with E plus m minus q phi acting on psi minus, this added together will give you 0. Now, let us use the non-relativistic limit once more. In this non-relativistic limit, I assume that E plus m minus q phi, that is actually roughly 2m. This is actually not very difficult to understand, that basically you are saying that the energy is mostly driven by the rest mass of the particle. So, E is roughly equal to m with c equal to 1, and I am assuming in the first iteration that the scalar potential is actually 0. The phi is actually 0. So, this E plus m minus q phi, this is roughly 2m. So, therefore, this second equation if you look into, this is essentially 2m psi minus plus sigma into I del plus q a psi plus equal to 0, and this simply gives you a psi minus, an expression of psi minus in terms of psi plus, and that is minus 1 by 2m sigma dot I del plus q a psi plus. Now, what I am going to do, that I am going to replace this form of the psi minus into the first equation. Okay? So, this is once again an algebra which you can do, and if you do that algebra, what you can see is that it will be E minus m minus q phi psi plus plus sigma dot I del plus q a into psi minus, which is replaced by this particular form, and so this is this particular form which is minus 1 by 2m sigma dot I del plus q a psi plus equal to 0. You do a little bit algebra and you come to this point that this is 1 by 2m sigma dot I del plus q a whole squared. Okay. So, there is a bracket missing here, this is I del plus q a and this is whole square, and then there is this term of q phi which is present here, psi plus is equal to E minus m psi plus. So, this looks like an nice eigenvalue equation, right, that we actually have. Now, what this equation does indicate? In order to understand that, what we will do, that we will use or rather do a little bit of more algebra using this Pauli spin matrices. So, for example, sigma dot A into sigma dot B, this is an identity which you should check, that this is actually A dot B plus I sigma dot A cross B. Okay. So, this is something that I am going to use, and use the fact that here in this expression what I essentially have is A is equal to B, which is actually I del plus q a. Now, importantly here, usually what happens, that whenever you have A equal to B, A cross B equal to 0, but A equal to B involving del and A, that A cross B will not be equal to 0. So, that you can calculate, because I have this quantity sitting here which is sigma dot A cross B. So, with A equal to B equal to I del plus q a, this quantity क्या है, I del plus q a cross I del plus q a, you can easily see that this will give you A cross del and del cross A. These are the two terms with a prefactor of IQ sitting, and psi plus anyway is sitting, on which this is actually acting. Now, the psi plus, in principle what we have done, that we have segregated the phase part, and psi plus is just a function of E and P, right? I mean, that is the idea. So, therefore, this A cross del, where this hungry del operator basically has to act on psi plus, has nothing to work upon, right, because psi plus is now a function of energy and momentum only. So, therefore, this contribution goes to 0, and this leads you that A cross B, where A and B both are I del plus Q A is nothing but I Q del cross A psi plus. Now, what is curl of A? What is curl of A? Curl of A is something that we are very familiar to, and that is nothing but the magnetic field or B. So, therefore, this term is essentially I Q B of psi plus. So, in a sense you can say that this term sigma dot I del plus Q A whole square acting on psi plus, this will essentially give you A dot B, which is essentially I del plus Q A square minus this term sigma dot A cross B, and that is nothing but it is going to give you minus Q B, okay, psi plus. So, this is what is happening, and here I have used this fact that B is curl of A and sigma I sigma j is delta I j 1 plus I epsilon I j k sigma k. So, therefore, what I basically have here, there is a bit of typo. I have to correct this one. This is actually just not Q B, this is essentially Q into sigma dot B. This is sigma dot B, because this is sigma dot B, right. So, this is what I have. So, now if I get back to this full expression, then what happens? So, I have this first term which is like 1 by 2 m I del plus Q A whole square plus Q phi, and this term that we actually did find out is going to give me minus Q by 2 m sigma dot B psi plus, giving you E minus m psi plus. Now, what does this term indicate? This term basically implies that minus Q by 2 m sigma dot B is simply, you can write that this is minus Q by m S dot B, where S is nothing but sigma by 2, right. I mean, S is nothing but the spin. Now, what is this term? This is nothing but mu dot B, where mu is the spin magnetic moment, and you can identify this mu to be Q by m into S, which once again from the generic definition you write it as Gs, which is the spin G factor into the magneton mu n into S, right. Now, this is Gs into what was the mu n? Mu n was Q by 2 m and into the S, and this whole thing is nothing but Q by m into S, correct. So, this whole term that you actually have here, Gs into Q by 2 m into S, is nothing but Q by m into S, which concludes that the spin G factor Gs must be equal to 2. Okay. Once again, to repeat that this term that you actually have in this equation is identified to be the mu dot B kind of interaction, and that mu is nothing but Q by m into S, as we actually find it out here, and that once I write it in a generic form like Gs into mu n into S, where mu n is defined as Q by 2 m, then the Gs, the spin G factor, is identically equal to 2. So, this is ideally what we actually think. So, this is the gyromagnetic ratio, and this is twice than the orbital motion, because GL is equal to 1 for charged particles. So, the Gs is equal to actually 2, and this is an important consequence of this construction of the QED or the Dirac equation with the photon interaction. So, experimentally what we usually do, that we measure this what we call the anomalous magnetic moment, or A, which is actually we try to see the deviation of this Gs from 2. So, we measure Gs minus 2 by 2, and at the tree level, or at when we are just taking this interaction like here embedded in it like gamma mu q mu into psi, that is actually giving me, this is what is called the tree level or the classical level. We expect this A to be equal to 0, but however, quantum mechanically that is not just the case. This is a very important point, and you basically say that this measurement of this particular vertex, which we wrote as minus I e gamma mu, right. I mean, this is not only this, but it has all the higher order corrections, the quantum corrections which people say, which basically has the possibility of emitting a virtual photon between these two vertices, and this is what is called the vertex correction. These will actually contribute. Or even if you take a higher order, then in this photon you can also have a fermion created and annihilated, a fermion loop in this one. So, you can have also a diagram like this. So, you basically have all these higher order corrections contributing to this what you call the spin G factor. So, this is coming from this absorption on a virtual photon, and one can actually show, if you do this calculation, if you want to do this calculation, I will suggest you that you look into the book of Peskin and Schroeder, where all these details are done. I do not have the provision of doing this calculation in details, this loop calculation, but basically once you do at least at the first loop order, then this is going to come out as alpha by 2 pi, where alpha is essentially the electromagnetic constant, the fine structure constant, and so therefore this AE turns out to be something like 0.0011614 at one loop level, and this was a famous calculation which was done by Schwinger in 1948, and this gives you an anomalous magnetic moment. So, what we are saying? We are basically saying, see, QED essentially allows the electrons to interact with the photon, and that interaction basically gives rise to the spin magnetic moment, and that basically tells you that the spin G factor must be equal to 2. But then we say that no, this is not completely correct, because quantum mechanically we cannot just rely on that vertex that we have taken, but it will have contributions from the higher loop order, the vertex corrections coming from one loop and two loop and so on. And at the one loop level, if you calculate, then basically it is coming out to be something very tiny, which is like 0.0011614. Now, you go to the experiment. You basically do an experiment where you use the electron spin resonance or ESR, and you find out that this small tiny deviation that you theoretically calculated, the AE theoretical minus AE experimental divided by AE theoretical, you know, of the order of 10 to the power minus 6 or even less, and this matches very well with the quantum electrodynamics calculations. So, all these loop level calculations are also an after effect of quantum electrodynamics, and so therefore, what you are trying to say that I have been somehow able to measure this very little tiny deviations in the anomalous magnetic moment to a great order of precision and match it with the experiments. So, here I give you a brief description of how exactly this is measured, and this is basically what happens, that you have to expose the electrons to microwave field within a strong magnetic field. When the microwave frequency essentially matches with the resonance frequency of the electron spin absorbing the radiation, the electron spin essentially flips. Now, what does it basically mean? That the energy due to the spin magnetic moment is given by mu dot B or mu z B, which you can say that this is Gs into q by 2m into msz into B. Now, this is Gs into q by 2m into plus minus half into B, because msz can take two values plus minus half. So, this basically splits the energy level into E0 plus mu zB and E0 minus mu zB. So, if the energy which is provided which is of the order of 2 mu zB, then essentially one can have a spin flip, and that will give you a peak in the electron spin resonance spectrometer. And so, this is the methodology by which you can measure the spin G factor very precisely, and that matches with this very precision calculation of the quantum electrodynamics. And although we have talked about other experimental procedures like E plus E minus going to mu plus mu minus, that has been measured. The other processes has been explained very nicely, E minus tau minus scattering, the other scattering experiments also. But this precision order with which your QED calculation matches with your experiment actually is one of the triumphs of QED, and of course, it was awarded with the Nobel Prize. There is one point briefly with which I would mention and end this lecture, that accordingly we expected the protons and neutrons to also have spin g factor to be equal to 2, but it was measured to be something completely different. For proton this was measured like 5.585, and for neutron it turns out to be minus 3.83, and these were the signs of the fact that these are not fundamental fermions. These are not fundamental particles which are fermions, but they actually may have some inner structures. Okay. So, this is another very important aspect of QED. With this we would like to stop today, and we are going to start a new topic, which is a weak interaction from the next lecture. Thank you very much, and I will see you in the next class. Bye.